Welcome back to ECE 320A. A lot of activity in the classroom, which means something must be happening. And there is an exam the next time you come to this classroom for a lecture. It won't be a lecture, it will be an exam. Exam number 1 is on Thursday. Tonight, homework number 2 is due, and also right after class, we're going to see if we can have our review session in this room. Just stay put. If somebody comes and kicks us out, we'll have to go looking for another room. We'll see how that works. Basically meaning I didn't officially request the room at 5. So we'll see. But here what we want to do today. This material will not be on exam number 1. This is Laplace transform material. Hopefully you can still stay focused and attentive to what we're talking about. We'll start with some properties, and that will lead us into looking at the Laplace transform of a derivative. Then we'll work through some examples and essentially trying to come up with a differential equation. And that differential equation will be connected to an electric circuit, and therein lies the quiz. How do you find a differential equation for a circuit? Is that a question?
Yeah. Is the review all of the notes of the actual lecture? Is that going to be on the top though as well?
The question was, will the review lecture be posted with notes and video? That's the plan. That's what I plan to do. If something hiccups, then maybe that won't be what happens, but that's what I'm planning to do. It will be treated similar to a lecture in terms of what's available to you after the occurrence of that event. We've taken the Laplace transform of a derivative. We'll then look at the Laplace transform of an integral. We'll derive some transform pairs. Essentially, what do you see in these tables of Laplace transforms? How can we go from the kitchen to the living room? How can we go from the time domain to the frequency domain? And we'll do that for impulse waveforms, a generic exponential, and then we'll say, oh, we'll go ahead and allow that exponential to be a complex exponential, and then we can write sines and cosines in terms of this complex exponential, meaning we can then find these transform pairs for sinusoids. What's the Laplace transform of a cosine? What's the Laplace transform of a sine? Eventually, we'll start looking at exponentially damped sines and cosines. I'm not sure how far we will get, but this is where we're headed. We'll then look at some operational transforms or some theorems. What does the Laplace transform do when you shift a waveform? I think we've already looked at that for a unit step, and we said this is what happens in general. The S translation, what does that mean? That is then associated with exponentially decaying or adding an exponential to another waveform in the time domain, and that then translates S in the frequency domain, and then we'll talk about scaling. We've already looked at the Laplace transform of a unit step and a weighted unit step. We've already defined the Laplace transform. Let me just state a couple of properties that are very critical or important or key to being able to go from time domain to frequency domain, and the first one is homogeneity. If you scale or weight a waveform by a constant, A is not a function of t, of time, it's not a function of f, A is just a number. If we weight this waveform f of t in the time domain, we can apply that exact same weighting on the transform of f of t in the frequency domain. That's homogeneity. And that's important to be able to do that. If you scale a waveform in the time domain, you have exactly that same scaling in the frequency domain. The other property, which I think you can guess what happens on the other side of that implication symbol. If we now add two waveforms in the time domain, superposition property of the Laplace transform allows us to do the same exact combination in the frequency domain, meaning now in the frequency domain, superposition allows us to combine in the same way that we did in the time domain these transformed waveforms in the frequency domain. Together, taken together, this homogeneity and superposition property, you could call those linearity properties. That, in fact, allows us to treat circuit elements, and in this class, think resistors, inductors, and capacitors separately. And we can then perform these Laplace transform operations on these individual or separate elements in a circuit, and that is the key. That allows us to go from the kitchen to the living room. From differential equations, which I think we said we're living in the kitchen, I don't know, don't hold me to all of these locations, and algebraic equations in the living room. Actually, I think maybe it was just, anyway, I don't remember. Go back and watch the video if you really want to make the connection or see if I'm wrong. But this allows us to go back and forth, and in fact, when we start doing inverse Laplace transforms, we'll want to go back from the frequency domain. What does that now look like in the time domain? So it's not so much we will get back differential equations, we will get solutions of differential equations when we go the other way. We'll want to solve for waveforms or functions in the frequency domain as a function of S, and then when we take that back into the time domain, it will in fact give us the solution to these differential equation problems. Or how do these differential equations arise? They arise from electric circuits. This is how we can now analyze electric circuits, is via the frequency domain approaches or using Laplace transform techniques. This, again, is a generalization of what you've been doing so far this semester with sinusoidal steady state. Sinusoidal steady state, you were always shaking. You were in a steady state behavior at some frequency omega. The Laplace allows us to generalize that and now have transients present in addition to possibly sinusoidal or persistent excitation in your system. That's the power of the Laplace transform. Let's look at that. So if we're now playing with differential equations says, oh, you have derivatives of waveforms, time rates of change of signals, somehow being combined to equal maybe a forcing function, or a forcing function is driving this linear combination of differentiated waveforms. What does the Laplace transform of a derivative look like? And really, this is what you'll want to be able to repeat now and later this semester and even beyond. Is somebody might say, what's the Laplace transform of a derivative in the time domain look like? And your response will be multiplication by S in the frequency domain. If you now knew, now I'm covering up that prime, if you knew the Laplace transform of F was capital F, now the Laplace transform of the derivative of F can be obtained by simply scaling or weighting that original Laplace transform by multiplying it by S. Now we have to adjust it by what this waveform looks like at time t equals 0 minus, and that's where we are doing this minus f of 0 minus. and that will be a number or an initial condition. That is the argument on that little f, or lowercase f, is evaluated at t, at time, equals 0 minus. In this expression, then, we have a frequency domain term, and we're subtracting a number. And that number is the initial condition on the waveform f. Where did it start? We're subtracting that off. Question?
Yeah, so you might be going into this. When you have second and third derivatives, so would you just basically square or cube the s, and what would you do to f? What would you have to add in or subtract as a constant?
Did everyone hear that question? Really? I have to repeat it for the listeners at home. The listeners at home, what the question was what if we start adding several more primes? What if we differentiate 2 twice or 3 times or 4 times? Does that simply mean we scale by s squared, s cubed? The short answer is yes. What happens to these initial conditions? That gets a little ugly. That gets a little bit more involved, and we'll work through some of those, but you'll be able to see those in transform tables, how that then works its way. So you'll have some of these, and they'll be weighted by different powers of s, these different initial conditions, and it won't just be the initial condition on the waveform. It might be the initial condition on its derivative or its time rate of change, or its second derivative, depending on how many derivatives you're trying to Laplace transform. I was hoping you had put on your 2-year-old hat and said, why is this true? That's what I was hoping the question was going to be, but you were way ahead of me. You were already in your junior year or senior year of college and said, what happens if we Laplace transform multiple derivatives? Well, that just means subsequent powers of multiplication by s. But let's now derive this relationship. You need to be able to use this relationship not only for a first derivative, but essentially iterate on it so that you can now do it for multiple derivatives. Let's look at the y behind this, or let's develop this expression, which is now saying we want the Laplace transform of the first derivative of f with respect to t. Or we might just say, well, that's the Laplace transform of f prime, where that prime is indicating the first derivative of f with respect to t. If this is what we're doing the Laplace transform of, we can simply replace or use that waveform in the definition of our Laplace transform formula. And the definition said that this is equaling the integral from t equals 0 minus up to infinity of the waveform itself, which in this case is the first derivative of f with respect to time. We scale that or weight that by this kernel e to the minus st, this complex exponential e to the minus st, and we integrate with respect to time. And we're assuming that little f of t, not differentiated, does have a Laplace transform. That the Laplace transform of f of t is well behaved, so we're assuming that it has already a Laplace transform. The assumption then that we're using is the Laplace transform of f of t is f of s. That's on the side of our paper. We're assuming that that's the case. Let's now go back, not all the way to second grade, but maybe a semester or more, and say, how do we get rid of, when we have inside an integral, if we have a derivative and we want to essentially kind of remove that derivative, because it would be nice if we could now rewrite this as an integral of f e to the minus st. Because we know that what that is, that's capital F of s. how do we go about getting rid of derivatives inside or in the argument of an integral? Substitution, that's one strategy that you learned in calculus. What's another one? Maybe that's not the one we're going to use here. Integration by parts, everyone's favorite, right? So now let's try to use integration by parts to make this happen. And what we will do is we will say here is one of our parts, and the other part is right there. Meaning one of these pieces, this piece, let's call that dw. Now I'm simply using w and v, and this part I will call v. And we are now wanting to do integration by parts, where we are letting v equal e to the minus st, and if that's the case, then we can differentiate that. And what happens when we what's dv equal to? We're differentiating with respect to t. It's now minus s e to the minus st dt. And w dw, we said, was what was left over. We wanted to essentially get rid of the f prime. dw better have that f prime, because then we'll end up with w, and that will give us this undifferentiated waveform for f. dw then is f prime of t dt. Or w now, if we take the antiderivative of both sides of that dw expression, we then end up with what we want, f of t. Where the integration by parts, if you've forgotten that, that's this integral of v dw. That's what we started with, this integral of v dw. That's now the integral of vw evaluated at its limits, which are 0, minus, and infinity, minus the integral of w dv. That's the math description of integration by parts. And we'll now substitute or use that to evaluate for the Laplace transform of the derivative. In our case then, let's go ahead and sort of rewrite that. This is now the Laplace transform of f prime of t. Using integration by parts, we now take v and w, which is e to the minus st f of t, and evaluate at 0, minus, and infinity. And we subtract the integral of w, which is f of t, dv, which is now this minus s e to the minus st dt. And let's evaluate the first piece and play a little bit with the second piece, so that the second piece might look like this original Laplace transform definition of f of t. What does s do when we integrate with respect to time? It's not a function of time, so we can pull that out of the integral. And we have a minus of a minus, that's going to give us a plus. Let's do the evaluation first. We now want to evaluate the first piece at infinity, so we'll say that this is now e to the minus s infinity f of infinity minus e to the minus s at the lower limit, which was 0, f of 0 minus, running out of space, but now below that is the minus minus, and the s comes outside the integral, and we now have 0 minus to infinity f of t e to the minus st dt. We said that f of t itself was Laplace transformable, which means it's well behaved. It now has a bounded value at infinity, and we're now looking at e to the minus s infinity. What does that do? That vanishes. What about e to the 0? That's 1. And now we end up with what we wanted. We now have minus f of 0 minus, and that was t equal to 0 minus, plus s, and what's in the last square bracketed expression is in fact the Laplace transform of the original waveform f, little f of t. Now if somebody needs you to Laplace transform the derivative of a waveform, then if you know the Laplace transform of the original waveform, you now know how to compute the Laplace transform of that derivative. Yes?
Is the reason why the Laplace transform of higher derivatives gets so complicated is because you have to do more and more integration by parts when you're trying to?
The question was the reason why it gets more and more complicated. Actually, it really only gets complicated in this initial condition piece. It gets nested. But the reason that it gets complicated is really just in accounting for the initial conditions. If you neglect your initial conditions, it gets pretty easy, and you just have to raise this power of s to whatever power the derivative was. Meaning if you had a second derivative, it would be s squared, capital F of s. And we will simply look at what this looks like when we apply it recursively. We're not going to start doing all of this by parts each time. Yes?
What are the conditions in which we could neglect the initial conditions?
What are the conditions when we can neglect the initial... what are the conditions under which we can neglect the initial conditions? It depends on the problem. And in some cases, if you simply want to know, here's a circuit, and I want to know what it's doing dynamically, well, maybe you don't need to know what its initial conditions are. You just want to know how does it behave naturally if somebody walked up and started shaking it. And when I say walk up and shake a circuit, I'm not meaning you're going to go into the lab, breadboard a circuit, and start shaking that circuit. What I mean is you're now going to connect it or energize it and hit it with some waveform. And you may not be that concerned with what the circuit is going to do specifically for a given initial condition and waveform. You want to know in general what will it do for any waveform. You could say, oh, we want the transfer function of this circuit, and then we can say we can neglect the initial conditions. That's one scenario where we might neglect the initial conditions. Let's now look at an example or an application of this Laplace transform of a derivative. Suppose that now somebody gives you x double prime, the second derivative of x with respect to time, plus 3 times the first derivative of x, plus 2 times the waveform itself, equaling v of t. And if you want to discuss this with someone outside of this class, you might just go home and say, yeah, we were working with linear time invariant differential equations this afternoon. Or you might just say, yes, we were working with LTI differential equations, linear time invariant. That's what we may refer to them as. And it is. It's a linear time invariant. Time invariant means the coefficients, the 3 and the 2, are not functions of time. It's linear. We don't have any products of x with x prime, or we don't have an x squared. We don't have a square root anywhere. We don't have a sine of x or a cosine of x floating around. It's linear. This equation is a linear time invariant, and a lot of times we just abbreviate that LTI. If you're texting, that saves you a little bit of typing. LTI differential equation. Now I assume that LTI is going to appear in many, many different texts after class. That's okay. That's why we're studying it. Now, what we want to do is apply what we just learned. We want to Laplace transform this differential equation. And we know how to Laplace transform x of t and v of t. We're assuming that those exist. And that just means hit the shift key. We simply capitalize v and say, let's now go into the living room and be in the frequency domain. That's now capital V of s. Likewise with x. We simply capitalize that if we're Laplace transforming it and say, oh, that's capital X of s. We're now in the frequency domain. What we do have to work on are these derivative terms. And we've learned how to do it for the one. Let's now see what happens when we try to do it twice. What we're doing then is we're Laplace transforming the left-hand side. And that needs to equal the Laplace transform of the right-hand side. We said that the Laplace transform was a linear operation. That means we can split all of these pieces apart. We can say, oh, that Laplace transform of the sum of the three is the same as the Laplace transform of the scaled combination of three. We have the Laplace transform of x double prime plus 3 times the Laplace transform of x prime plus 2 times the Laplace transform of x equaling what we said would happen if we Laplace transform v of t. It's scaled by 1. We're just going to say, well, that's equal to capital V of s. And now let's utilize that formula that we just derived for Laplace transforming a derivative. And let's not do two at a time. We don't know how to do that. Let's just do it one step at a time. If we Laplace transform x double prime, let's just Laplace transform that down to an x prime. Meaning, if we now Laplace transform x double prime down to x prime, we say, oh, that's s times the Laplace transform of x prime of t. What else? Now we have to subtract off the initial condition. And what initial condition are we subtracting off? The first derivative at time t equals 0 minus, because that's the f that we end up with. This is now x prime of 0 minus. Everybody comfortable with that first piece? We've simply Laplace transformed the second derivative, but we haven't finished yet. We want to do one more step so that we don't have this Laplace transform of a derivative. But we can keep going with the second term and say, oh, plus 3 times the Laplace transform of a first derivative, and that directly falls out of the expression that we derived. That's now s times capital X of s minus x of 0 minus plus 2 times capital X of s equaling v of s. What we now need to do is Laplace transform a derivative, and we know how to do that. But we have to keep track of all of these initial conditions that now are growing. And you were asking maybe what happens when we do the second derivative. Now you're going to find out. We now multiply by s. The Laplace transform of a derivative, well, that's just s, capital X of s, minus x of 0 minus x prime of 0 minus. And now let me pull some of these pieces apart. We have 3s x of s minus 3x of 0 minus. I'm distributing the 3 across those two terms, plus 2 capital X of s is equal to v of s. And what I want to do now is collect terms. I want to factor out all the terms that contain this capital X of s. I want to factor out all the terms that involve capital V of s. And I will then have terms that contain initial condition pieces. And here we had a second derivative, and you can see that we have the initial condition on the original waveform and an initial condition on the first derivative of that waveform. Here we now say, oh, if we're collecting terms, we now can collect, we have an s squared that weights capital X, we have a 3s that weights capital S, and we have a 2. We have a couple of terms that contain x at time t equals 0 minus. Magic. Something electrical is happening, and I have no idea how to fix it, or even what happened. Maybe did somebody move the wrong way? Everybody stay put, and we'll be okay. I don't think that was in the video, so they're going, what in the world? What did he pull this time? There's something messed up with this screen up here, and I'm glad you can't see it. It's about to throw me over the edge. It just flickers and flashes. No, I can't turn this one off. I don't, but well, maybe I can. Ooh. Now I have no idea what I'm doing, but let's keep going. This is now s plus 3 times x of 0 minus. Did I get the right factors weighting x at time 0 minus? I had an s times x of 0 minus with a negative sign, and I had a minus 3 times x of 0 minus. I'm factoring the minus out from both terms, and I end up with minus the quantity s plus 3 x of 0 minus. I have a minus x prime of 0 minus, and that all equals capital V of s. Eventually what we will want, you'll see how much patience I have or don't have. But what we want to do is eventually find little x of t. What's x of t the solution to this differential equation? That means we need to solve for capital X of s, and eventually we'll inverse Laplace transform for capital X of s. Let's now solve for capital X of s, or isolate that, by dividing every term by this polynomial that's weighting or scaling capital X of s. This expression that we now have written, we can rewrite as capital X of s, and I'm going to sort of group this into two pieces. One piece will involve capital V of s, and another piece will involve all of my initial conditions. And I'm putting everything to the right-hand side. Or I now have s plus 3 times x of 0 minus plus x prime of 0 minus all over s squared plus 3s plus 2 plus capital V of s all over the same polynomial, s squared plus 3s plus 2. Our Laplace transform we defined to be from t equals 0 minus to infinity. And we'll call that a one-sided. We're on one side of t equals 0. We're on the non-zero side of the time axis. Because we're dealing with one-sided transforms, we have a unique inverse. If we're agreeing in this class to only be doing one-sided Laplace transforms for t non-negative, t 0 minus to infinity, then we can find the unique little x of t associated with this capital X of s. Let me try to write that down. The one-sided by that, t is, I have eyes in the back of my head. I can just feel something not displaying. Goes from, that's the one-sided behavior that we're interested in, or that we're doing. The one-sided Laplace transform is unique. Which really is another way of saying that given this capital X of s expression, or this formula for capital X of s, we can find what it looks like in the kitchen. We can find little x of t. We can find its time domain pair. And the notation that we will use for that inverse Laplace transform is to simply say script L with an inverse operating on capital X of s gives rise to little x of t. And from our example, here's what we had for capital X of s. Do you see that I've actually put this into two pieces? And those two pieces are specifically collected in this way. One piece contains initial conditions, and one piece contains the forcing function, or what we were exciting, or what we were using to shake that differential equation. So we're having our answer, capital X of s, or inverse Laplace transform, little x of t, is made up of two pieces, of two parts. One part coming from initial conditions, so if we have zero initial conditions, we wouldn't even have to worry about that piece. And the other piece is a result of the forcing function, or how we're shaking that differential equation, what little v of t was doing to our system, or differential equation. There's the notation, and from our example, x of t, which is the inverse Laplace transform of capital X of s, has two pieces, or two parts. One part is the inverse Laplace transform due to the initial conditions. and the other piece is due to the forcing function. And we can make that maybe a little bit more explicit by just separating those two into a product. We have 1 over s squared plus 3s plus 2. That's the behavior of our differential equation. And then we apply to that in the frequency domain the waveform, its Laplace transform. This piece right here is due to the initial conditions, or the response. And this piece is due to our forcing function, or what's exciting the circuit. So we have two different parts to this complete answer for what is our solution to this differential equation. What is x of t, little x of t? Now you're ready to go. Now you're ready to show me what you can do with what we've learned so far. Here's the quiz, and I want you now to write or find, I might say, find the governing differential equations or equation for the following circuit. Here's a circuit with a voltage source, V of t. It has an inductor, it has a resistor, and it has a capacitor. And I want you to find the differential equation or the differential equations that govern the dynamic behavior of this circuit. Pardon? I think you've probably seen this circuit many times, and you may see it even more times. Maybe you can write the differential equation down in your sleep, but now put it down on paper and see what you have. What is the differential equation, or how do you begin that process? What I'm wanting you to do in this quiz is find the governing differential equation. Or I might even say, give me coupled differential equations. If the differential equations are coupled or connected, but they have to all be coming from or arise from this particular circuit. This circuit should have a certain dynamical behavior depending on the values of R, L, and C. And how that circuit behaves in response to V of t. V of t is just a generic waveform. I'm not specifying what that is. Now I want you to be able to go up and shake it in many different ways. And so I want you to leave V of t alone. Just say, oh, this is how I'm exciting this circuit. If this is the voltage source, here's the V of t that describes that voltage source. Are we finished deriving that governing differential equation? Put your name on your paper and hand it in. I'm full of surprises, aren't I? Getting you ready for the test. Boy, that's a big piece of paper. Am I serious? I'm serious to have you try to find the differential equation. Whether or not I collect the paper is another thing. So you can work together. You can I'm just wanting you to start thinking. Get the cogs moving so that you can have a little bit more appreciation for what we talk about later.
Theoretically, it's the Laplace transform, inverse Laplace transform of each component summed up, correct? That should give you a differential equation.
So what I want you to do is come up with the time domain differential equation without worrying about Laplace transform just yet. So what I want you to be able to do is, in an interview, if somebody interviewed you and said, oh, can you show me how this circuit behaves dynamically? You can say, oh, sure, let me derive the differential equation or the equations that govern the dynamic behavior of this circuit. And then you're going, and you're trying to think on the fly in real time. You're going, how can I keep thinking and showing sort of what I know about? What kind of a differential equation are you expecting? A first order, a second order, a third order, a fifth order? What kind of a differential equation would you expect to come out of this particular circuit? Do we have a clue? Is there anything in that sketch of this circuit that helps inform our thinking about, I need to derive something, what's it going to look like? And maybe your interviewer just says, can you tell me what this might look like in a general mathematics class? Give me a generic differential equation that will eventually, we will be able to show is connected or associated with this circuit. And what does that tell us? All right. Did anybody get an answer? Yes? Do you want to come to the board? I'll let you display it on this screen. I'm kidding, actually. I don't know how. Well, I guess I could have you write on the tablet, and then you'd be in infamy, right? You would be on YouTube. Your handwriting would be on YouTube forever. Which may not, well, anyway. So what kind of equation are we looking for? Do we have an idea? What? First order. How many think it's a first order differential equation? Show of hands. Be brave. How many thinks it's a second order differential equation? How many think it's a third order differential equation? How many think it's a fourth order? Sixth order? Where are we coming up with these orders? I'll have a hamburger and some fries on my order. This is the order of a differential equation. I'm hungry, obviously. I'm thinking of another order. But how do we figure out the order of this? We have two time-varying components, or what I like to call two energy storage devices. Right? We have a capacitor, that stores energy in the electric field. We have an inductor, and that stores energy in the magnetic field. We have two energy storage devices. And that is saying you should end up with a second-order differential equation. Let me write that down. We have two energy storage elements. Or devices. And that now says that we should be expecting a second order differential equation. And if somebody said, oh, what's the generic expression look like that might arise from that circuit? And now you say, well, I have two energy storage devices. Let me write down a generic second order differential equation. Linear, time invariant. So you might say, oh, it's alpha 1 V sub c double prime of t. What's V sub c? Let's just call that the voltage across the capacitor. That's V sub c of t plus alpha 2 V sub c prime of t plus alpha 3 V sub c of t equaling, let's just say, beta V of t. And if somebody said, oh, wow, you kind of know your theory, that would be a valid answer. If they said, give me a generic differential equation that will result from this circuit or appear from this circuit. Now, how do we start finding this equation? How do we find our alphas and our beta? What if we go back and we say, well, if you labeled this as the capacitor voltage, wow, a little aggressive with my eraser. There's the capacitor voltage. That's one variable that we probably want to write these equations with respect to. Another one might be, and these are actually coming from Eli and Ice. So this Eli and Ice is giving you a lot of power or information just in knowing Eli and Ice. If V sub c from Ice, if the voltage in Ice is important, and Eli is saying it's important, what's important with respect to the inductor? Its voltage or its current? The current, because of Eli, the I, right? So now if we were looking to write two first-order coupled differential equations for this circuit, we would probably want to write those in terms of this inductor current, I sub L. Yes?
We had a circuit that kind of looked like this, but it had like two inductors and two capacitors. Would we combine them into an equivalent one first and then find the order?
The question was, what if we had two inductors in a circuit and two capacitors in a circuit? It depends on how they're interconnected. If they're all in series, you could basically find an equivalent inductor and an equivalent capacitor for those. But if they are in some weird configuration where some parts are in parallel, some are in series, then you may actually have a fourth order circuit. You may have four energy storage devices that are interconnected independently in a sense, and so now you would expect a fourth order differential equation. It really depends on how they are interconnected. Here I have a series connection, and so I really only have one inductor and one capacitor that are the two energy storage devices. And if you wanted to think of this, you could say, well, I really liked 220, and there we focused mostly on resistors. And if you got into an interview and they said, we'll solve this circuit, you might say, I'm a little rusty. Can I replace these energy storage elements with resistors? Just to get yourself starting, right? Then you could write a KVL equation. And all of those resistors are in series. You could have an equivalent resistor, so you now have a voltage source applied to a single equivalent resistor. That's maybe how you might get started thinking. You want to kind of start moving slowly, and by the end you're going to be sprinting is the hope. Well, if we write KVL, what pieces do we have? Well, we could have, for some reason, I'm being fond of this eraser. So let me move this one over here and say this is I sub L of t. And let's say that this is now our voltage across that inductor. Here is our voltage across the resistor. And we've already labeled our voltage across the capacitor. And now do you see that we can write a KVL equation in terms of those variables that we've defined? We can now from KVL say, oh, we have minus V of t plus v sub L of t plus v sub R of t plus v sub C of t equals, what does it equal? Now we're back where we started, so that KVL needs to equal 0. And now what we will do is we have what, 4 variables that we've introduced, and we know it's a second order differential equation. We need to start getting rid of some of these variables. And the way that you can do it is be guided by Eli and ICE. You can say, oh, he said we should focus on inductor currents and capacitor voltages. If that's the case, can I start to rewrite these in terms of those variables? Here's the capacitor voltage. That's easy. I'll just leave it alone. But we have ICE and Eli. Let's look at Eli first. Eli says that V sub L of t is equal to L di sub L dt. Well, there's a way to get rid of that one. And now we have it in terms of the inductor current, which is a good thing. And what about ICE? ICE says that I sub C of t is equal to C dV sub C dt. But what do we know about the inductor current and the capacitor current in this particular circuit? They're the same, aren't they? It's series. So the current flowing in this circuit is the same. So anywhere I had an I sub L, I could replace it with I sub C. If we do that a couple of times, we'll actually be able to get rid of everything in here except V sub C and its derivatives and V. Let's do that. Suppose we now start to fill in some of these pieces. Minus V of t is equal to, plus V sub L is L di sub L dt plus R times what? I sub L, inductor current, if that's what we're thinking about, plus, well, we said V sub C of t was okay, and there we are. But now we said that I sub L and I sub C are the same in this circuit. It's a series circuit. So if I sub L is the same as I sub C, now we can get rid of that I sub L there and here by replacing it with an expression in terms of the capacitor voltage. And let's see what happens. The third term is going to be R times C dV sub C dt. We'll get a first derivative. The second term, L times d by dt of C dV C dt. Do you see that we've nested derivatives? We're going to end up with a second derivative, and there's our second order differential equation. Can I do that? Let's now say we have minus V of t plus L d by dt of C dV C dt plus R C dV C dt plus V sub C of t is equal to 0. L and C and R are time invariant. They can slide outside of these derivatives. Now we have the second derivative of V sub C scaled by LC. We can say we now have LC times v sub c double prime of t plus rc times v sub c prime plus v sub c of t equaling v of t. Structurally, that should look similar to this alpha 1 v sub c double prime plus an alpha 2 v sub c prime plus an alpha 3 v sub c equal beta v of t. We now have a second order differential equation in terms of v sub c, and if somebody wanted to rewrite that, meaning if they wanted to normalize it or make the leading coefficient 1, that will give us a monic polynomial when we take it into the Laplace domain or the frequency domain. Let's divide all terms by LC, and we now have v sub c double prime plus, we're dividing RC by LC. The C's cancel, and we have R over L v sub c prime plus 1 over LC v sub c of t equaling 1 over LC v of t. Another equivalent second order differential equation. And now we know how to Laplace transform that and take it into the living room, into the frequency domain. If we started with this in the kitchen, in the time domain. Questions on that? Since we were so successful there, let's look at another circuit. Yes? Is this what you had, actually, before you...
I did the current version, but so
You did the present version? Oh, oh, the current version. Oh, like flowing electrons? Yeah, okay.
is that interchangeable with this?
So you did for I sub L of t for the inductor current.
Well, I did the voltage, the KVL, but using in terms of currents.
KVL in terms of current. You should be able to find other equivalent expressions for this circuit. We could have written it as two coupled first order differential equations, one in terms of the first derivative of I sub L and one in terms of the first derivative of V sub C. Let's now look at another RLC circuit. Suppose now we have a current source, I sub G, and we actually have a switch. And suppose that we throw this switch open at t equals 0. And before t equals 0, that switch is closed, and connected to that is an inductor, L, and a resistor, and a capacitor. And we want to model this for time t greater than or equal to 0. And based on our discussion before, you can start to anticipate. So after time t equals 0, we don't even have to worry about that switch branch. It's gone. It's opened up. And we then have this new circuit that has a current source driving this combination of L, R, and C. It's in parallel with that inductor. Pardon? And so now what are we going to end up with here relative to the generic behavior? What would you say is happening in this circuit? Or what do you hope to end up with as an answer? If I said, oh, describe this circuit's behavior in the time domain, what would you expect to end up with based on what we talked about before? How many energy storage devices do you have? 2. So you would expect a second-order differential equation or 2 coupled first-order differential equations. That's equivalent to 1 second-order differential equation. We have 2 energy storage devices. And that now says that we have a second-order differential equation or 2 first order differential equations. And we can always rely on our friends, Eli and Ice. Eli tells us that the voltage across the inductor is proportional to the time rate of change of the current through that inductor, or it's L, where the proportionality constant is L. It's L di sub L of t dt. And Ice says that the current through that capacitor is now equal to or proportional to the time rate of change of the voltage across that capacitor. And based on what Eli and Ice tell us, which is we probably need to focus on the variable in the last variable in Eli and Ice, we may want to write these equations in terms of capacitor voltage, V sub C, and inductor current, I sub L. If somebody says, oh, pick some variables, those are usually good ones to pick, to rely on. Let me write that down. Usually, best to write differential equations in terms of inductor currents and capacitor voltages. From Eli and Ice. If that's the case, we might come back up here and say, oh, here is I sub L of t, and here is V sub C of t, and how can I now use those to my advantage? And now, what might be a little bit of a twist on what you're used to seeing, we're going to actually write not 2 KVL equations or 2 node voltage equations. We're going to write one of each. And the reason we're going to do that is because that may actually allow us to write equations in terms of these variables of interest. Suppose we first want to write a KCL at that node. Let me call this node A and say, okay, let's write a KCL equation at node A. Now I'm trying to algebraically sum currents. Or I say currents going into A need to equal the currents going out. And this is for t greater than or equal to 0. We have no concern over that switch branch. It's gone after t equals 0. We have Ig going into A. We have I sub L coming out. And what's going through R and C as far as a current is concerned? Can we write that current in terms of these variables of interest? We have some dynamics going on because we're dealing with a circuit. But we simply need this current, don't we? And isn't that current I sub C? And don't we know how to write I sub C based on ICE in terms of V sub C? Meaning KCL at A we can write as the current in is the current source I sub G equaling the current out, which is I sub L plus I sub C. I sub L is what we want to write these expressions in, so let's just leave that alone. But now we can say, oh, I can rewrite I sub C based on ICE. And that's plus C dV sub C of t dt. And now you can see the coupling that we have. We have the inductor current coupled to the capacitor voltage in this first order differential equation. And Eli, if we used Eli, what would that produce for us? What does Eli tell us? What variables does that connect in this circuit? It tells us the current voltage relationship of the inductor. And what does the voltage of the inductor give us? That actually gives us the voltage at A, does it not? And that's typically what we like to think of when we're writing KCL equations, is maybe a voltage at that node. Eli then allows us to say that V sub 1, or now I'm calling this V sub 1, or there's minus and plus, V sub 1 is now equal to L di sub L dt. What? We have I sub L. Can we solve this Eli for I sub L? We can integrate that, can't we? So we can now find I sub L in terms of V sub 1. Or we now have I sub L of t is equal to 1 over L integral V sub 1 of tau d tau. Actually, this is not to infinity. This is just up to time t. So if we wanted to write this in terms of voltages, if somebody said, oh, I want this in terms of voltages, here is V1 at the first node, and right here could be V sub 2 or V sub C at the second node. And now you have these two voltages. If you say, I don't like mixing currents and voltages, let me just write this in terms of voltages, you now have a way of doing that relative to using this I sub L. You can now say that I sub G of t is equal to I sub L, which is 1 over L integral from 0 minus to t v1 of tau d tau plus c dv sub c of t dt. And now we have something that involves just node voltages. Not currents and a voltage, but two voltages. What if we now said, can we write another equation? And another equation might be to write a KVL equation in mesh B. And that's what we want to do next, which is going to be, how will we write that? If we write KVL around B, we're now going into minus V1 plus V sub R in that direction, which would be R times I sub C, the way we've labeled I sub C, plus V sub C. But I sub C or I sub R is C dV sub C dt. You see how we're getting all of these differential equations or these time rates of change equations for a given circuit? We'll have to pick up with that fun after exam number 2, and we'll stop here at that point.